Okay, so let's say we have a charged particle here of charge Q naught, and it lives in an electric field, or suddenly we turn on an electric field, and so there's an electric field here, say that way, and we don't know what its value is, but we know that there's so there's an electric force. Right, what follows from this is that there's an electric force Q naught times the unknown electric field, which will speed up the particle. So let's say that the object, the charged particle, starts at rest, and it gets sped up by this electric force, Fe, and it travels through a region from here to there, let's say, over here, where the electric potential difference has magnitude phi. So phi, or let's specify it, phi star, specified further, phi star is the magnitude of the electric potential difference. So, right, minus E dot dr is the integral of the electric field from here to here, and we want the magnitude of that. So that's what sometimes we refer to as the voltage difference. Right, there's a voltage difference there. And the question is, how fast is the particle going when it gets here? So here's the particle. What's the speed of the particle if it starts at rest there? And so here all we have to do is to apply the work-kinetic energy theorem, where the right-hand side is the final minus the initial kinetic energy, which of course is just 1/2 times the mass. So let's specify the mass. Let's say it has mass m naught. So the final kinetic energy is 1/2 m naught times the unknown speed squared minus the initial, which is 0. Right? The particle starts at rest, so it has 0 kinetic energy, and that's the right-hand side of the work-kinetic energy theorem. So the left-hand side requires figuring out the work, and so all we need is to recognize that we're looking for a force times distance kind of quantity, but we have to write that in terms of electric potential, and so the work in this case is some positive quantity, so we'll throw in all positive values. We don't have to worry about the direction of things. So it's not just the magnitude of the electric potential difference, right? That's a work per unit charge, so we need to throw in the charge, which in this case is Q naught. And so we have Q naught phi star equals 1/2 m naught v squared, and so the final speed at this point is 2 Q naught phi star over m naught square root, and we take the positive value of that.